I would now like to introduce Michael Taylor for his talk, Advances in Genomics Explain Medulloblastoma Behavior at the Bedside.
Great. So I'd like to thank Russ for the invitation to share a little bit of our work with you today. So medulloblastoma was described by a neurosurgeon, Harvey Cushing, about 100 years ago, just under. And the way Harvey would diagnose a medulloblastoma was he'd have a kid with a posterior fossa tumor, and he'd go to the operating room and he'd crack the back of their head open, and he'd take a piece of the tumor out and he'd walk it down the hallway to his pathologist, and they would stain it with H&E, and they'd look at it under the microscope and they'd say, "Harvey, that's medulloblastoma." And the way most of you diagnose medulloblastoma in your practice in 2016 is you get a kid with a posterior fossa tumor, you crack the back of their head open, you cut a little piece of it out, you walk it down to your pathologist, they stain it with H&E, and they say, "That's a medulloblastoma." How bloody depressing is that? Who here would want to fly on a 100-year-old airplane, or carry around a 100-year-old cell phone, or drive a 100-year-old car? So why has everything else got so much better and gone fast and forward so much, but we're still doing the same bloody thing that Harvey Cushing did? Over the last 5 to 10 years, it has become apparent, though, that medulloblastoma does not exist. That really it's a conglomerate of molecular entities that look the same under the light microscope, but are really very different diseases. And in fact, we know now that there are molecular subgroups of medulloblastoma, and many of you are going to be hearing about this in your practice or at your tumor boards. And we also know that no matter where you are in the world, if you're in India or Canada or the United States or Japan, no matter where you are, these same things hold true. And we know that there's good groups that do really well, and we know there's groups that do really poorly. So for example, if you have one of these blue Wnt medulloblastomas, you are going to survive your disease. And in fact, if you die, it's probably because the surgeon screwed up, or you got a late radiation-induced glioblastoma from your tumor. Whereas if you have one of these yellow tumors, which you can see do poorly all over the world, you've got a very good chance of dying no matter how aggressively we treat you. This has been recognized now by those of us who work in this medulloblastoma space, and we've published consensus papers, and we recognize that there are 4 medulloblastoma molecular subgroups. The Wnt subgroup, these are patients that almost all survive no matter what we do to them or what we don't do to them. A sonic hedgehog subgroup, and a much less interestingly named group 3 and group 4 subgroup. You are going to be hearing about this if you take care of these patients, if you haven't already. This is coming to a hospital near you if it's not already there, and it is going to be the basis for the next round of clinical trials at the Children's Oncology Group and at PSYOP in the near future. The problem being that in the past, a lot of these tests were done in research labs, and you cannot rely on a research lab test to make a clinical diagnosis, because we might have screwed up, right? Maybe we didn't have our coffee and we pipetted the wrong thing, or we took the wrong tube. So it must be done in a CLIA-approved setting. So the tests must be done in a clinical lab. In the past, this was a problem at sick kids, but I'm happy to say for the last year or so at sick kids, when I operate on a kid now, or my boss, Jim Rucka, operates on a kid, we take the tumor out, we get the histology-based diagnosis back, but then within a week, we also get the molecular-based diagnosis back. So we get all the histology nonsense, small blue cell, blah, 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 100-year-old garbage, and then underneath it says, molecular biology says this is a group 3 medulloblastoma. So this is moving forward. We have this in Toronto. It's available in a few places in the United States. It's going to be at every place in the United States very soon. There is no such thing as medulloblastoma. It's a human construct. I like to say, what do the Loch Ness Monster, the Sasquatch, and medulloblastoma have in common? None of them exist. They're all things made up by humans, right? This is really a group of different diseases that we've all lumped together that does not exist. So I do a lot of that kind of research in my lab, but I realize that even if every kid walked into my clinic and he had a best before date on his forehead, said, "I'm going to die on October 15th, 2017, I still wouldn't have helped a single kid. So I wanted to figure out what we were doing that was helping and what wasn't helping. And particularly, I was interested in surgery, particularly surgery for neurosurgery. So I gathered up about 800 medulloblastomas from around the world, where I had very good data on extent of resection, all their adjuvant therapy, and good molecular data. And I thought that there at first that there would be a difference in the amount, the frequency of extent of resection or gross total resection based on subgroup. Turns out I was wrong, as shown in this slide here. It turns out that the extent of gross total resection doesn't vary that much by subgroup. So then we looked at survival. And just like so many papers before, if we did not account for molecular subgroup, we saw that gross total resected patients did better than patients who didn't get a gross total resection. However, once we did a multivariate analysis, as I'm showing here, and we accounted for molecular subgroup, the effect of gross total resection went away. There was absolutely no difference between gross total resection and near total resection, and there's actually a very small difference between near total resection and subtotal resection, right? So we've been kidding ourselves for a long time now, and I think we've been hurting children by doing overly aggressive surgery that did not need to be done. Okay, and anybody who wants to read this was published this year in Lancet Oncology. You can read all the details. I am not saying that we don't need to operate on these kids. We need to operate. We need to reconstitute the CSF pathways. We need to establish a tissue diagnosis, right? We need to remove mass effect on the brainstem. And in most cases, I do think we can get a gross total resection. But we should not be hurting children. We should not be giving children seventh cranial nerve palsies and extraocular muscle palsies to go from a 98% resection to 100% resection, because it does not have any effect on their oncological care. It does not. And we have to start changing that, right? Because we're not doing these operations so that we can look at a tumor board and be proud and point at the post-op MRI. We're doing this to help the kids. So I told you that there's 4 molecular subgroups of medulloblastoma, and there were some people that were really, really annoying me because they said that the bad subgroups of medulloblastoma were just sort of like an end-stage progression of the disease. And that if we looked at advanced disease, it turned out that maybe all the medulloblastomas are group 3. Turns out that's not true. Subgroup is very stable. And this is one of the more important slides I'm going to show today. This is 3 different cohorts of patients who all died from Toronto, mixture of North America, and these ones are Russia. A solid bar means a local recurrence, and a stippled bar, or crosshatch bar, means that the tumor has recurred metastatically. So these red sonic hedgehog tumors, which principally occur in adults and in infants, do recur locally. And maybe we need to pay more attention to them surgically. But you can see that the group 3 and group 4 patients, which together make up 2/3 of medulloblastoma patients, all recur metastatically. These kids are all dying of the Mets. They're not dying of the primary tumor, right? So who here in the room really believes that they're helping cure metastatic disease by taking out the posterior fossa tumor? Who really believes that? I hope none of you. And not only that, but we don't really know much about metastatic disease, right? Because we all know what metastatic disease is in medulloblastoma, but the reality is none of us ever study it, right? Because it's on the surface of the brain. And I don't care if you're Yassi Yassergill, you ain't scraping that off the surface of the brain. That's like butter on hot toast. It is not coming off surgically, right? And this is what's killing the patients. And this is what we're really principally treating when we give experimental therapy. But having said that, almost all the research that's been done is on primary tumor because that's what we take out in the operating room. So my laboratory, I won't belabor the details, made mouse models of medulloblastoma that were metastatic. And when we did that and we looked at the genetic events in the metastatic medulloblastoma, in the Mets, and we compared to the genetic events that were occurring in the primary tumor from the same animal, we saw that the overlap in the genetic events was less than 10%. Right? So let's say that my raison d'etre was to cure mouse medulloblastoma, and I did all this research just so I could cure mice. If I had developed some sort of therapy by studying the primary tumor, the odds of my therapy working in the Mets would be 10%, right? But those are mice, they're not humans. But it turns out when we now move to those rare cases where I'm able to get tissue from the metastasis and from the primary tumor from human children, it's the same thing. You know, this is a very simple example here using an old school technology. Harvey Cushing probably would almost approve. NMIC is amplified in the primary. It's non-amplified in the same patient's Mets. same thing here, right? And we see the same thing if we do sequencing, if we do CpG methylation analysis, whatever we do, the Mets are very, very different from the primary tumor. I started to get really scared though. I was worried because I know that every kid who walks into my clinic, they don't have one Met, they have multiple Mets. In fact, and sometimes their whole CNS is covered in Mets, right? And I was worried that every kid who walked in the door didn't have two diseases, a primary and metastatic disease. I was worried they had 37 diseases. And I was going to quit and move to Whistler and become a lifty and just ski for the rest of my life. But then we got a very small number of cases where we were able to compare multiple metastases from a single child to the primary tumor. And it turns out all the metastases are very similar to each other. So every kid, if you're a pediatric neurosurgeon who walks into your clinic, really has two diseases: that primary disease that we can take out and a metastatic disease that we don't take out, but in the near future we're going to have to biopsy. So leptomeningeal metastasis diverge in their biology from the primary tumor. The early evidence, mostly from my laboratory, says that the multiple Mets are similar to each other. In the future, if we're going to be doing targeted therapy, if we're on clinical trials of biologics, neurosurgeons are going to have to start biopsying the leptomeningeal disease. It's not a fun operation, it's not a glamorous operation, but it's something that we're going to have to start doing. There is another very silly assumption that we make in neuro-oncology, and that is all of the research that's done is done on primary tumors before therapy, right? All of it. We sequence primary tumors, we have mouse models of primary tumors, we have cell lines and xenografts from primary tumors, but all of the drugs that we test them on children with very highly treated disease, who've been radiated, who've been chemotherapized within an inch of their life, right? And we do this based on the assumption that the disease is similar and stable over time. So I wanted to test that assumption. So I got my postdoc, Livia Garcia, and she took our mouse model of medulloblastoma and she put the little mousies under anesthesia. And over time, she learned how to do a little craniotomy on their posterior fossa and take out their tumor. For a long time, all the mice died, and she was very discouraged. And eventually, she learned how to do this, and she gives them steroids and post-op fluids and a warming pad, just like we treat our patients. And she was really angry at me for a year or two because things weren't going so well. And I said, Livia, you should be really happy, because none of your patients, at least their parents, that is, none of the parents of your patients have your cell phone number or email address like mine do. After these mice have recovered from having their microneurosurgical removed of their medulloblastoma, we then use a CAT scan guided collimator to give them fractions of radiation, just the same way we give to human kids. And you can see we've done this properly because as opposed to human children who go bald when we radiate them, these mice go gray, as you can see along the spine here and along the head. And when we do that now, we have the opportunity to have tumor before radiation and after radiation. And when we do that, what we see is in the mice, the genetic events at the recurrent tumor and the primary tumor only overlap by about 10%. So that means if you're going to only study primary tumor and use your genetic, use that genetic information to plan therapy at recurrence, you've got a 1 in 10 chance of the target still being there. And since there's 15 to 20 kids in an average phase 2 trial, that means you're going to have 1.5 to 2 kids who actually still have the target, whether or not the drug works and whether or not the target is still necessary for maintenance. That is mice. But now when we sequence these rare humans where we have primary disease and recurrent disease, be it in the posterior fossa or be it metastatically, and we do whole genome sequencing, we see the same thing. So all of these clinical trials we've been doing have been a complete waste of time because none of the targets were still there anymore. They were all gone. We're shooting up in the air and the ducks have flown by like 10 minutes ago. When we do look at the events that are in the recurrent tumors, we see that the predominant event, both in the mice and unfortunately in the humans, is mutation of that well-known tumor suppressor gene P53, which is good news and bad news. It means that we know what we're doing and we're finding the right thing. But it also is kind of bad news because P53 is very difficult to target. But it did give me a chance to invent a new profession. I think I'm the world's first Drosophila radiation neuro-oncologist. So we made Drosophila that get neuronal brain tumors. They have an overproliferation of the neurons in their brain. And we did this either on a wild-type background or a P53 mutant background. And then we radiated the flies. And we didn't need this nice, 18 fractions of 2 gray thing. We just zapped those little guys. 40 gray in one dose. Bang. Right? And when we did that, what you can see here is the wild type flies who don't have a p53 mutation, their tumor was very well treated by the radiation, whereas the ones who have a p53 mutation were not. So there's this saying, right? I've just told you that for the last 30, 40 years at the Children's Oncology Group in North America, everything we've done has been based on this idea of studying tumors up front, right? Based on the idea that cancer is static, and then using the drugs that we discover at recurrence after the tumor has changed. So there's this saying in English that if you give 1 million monkeys, 1 million typewriters for 1 million years, eventually they will rewrite all the works of William Shakespeare. That apparently is the approach at the Children's Oncology Group right now. I'm tired of that, right? I'm in my mid-40s now. I would like to see some progress in this field before I retire. We must stop this. We must start addressing heterogeneity through time and space. Medulloblastoma changes over time, and if we don't account for that, we'll never get anywhere. Those are my funders, and that's a picture of my lab, and thank you very much.